Archimedes was a notably smart man within ancient times for his advances in mathematics, such as surface area and a volume of a sphere, and his various inventions throughout his lifetime. Born in 287 BC in Syracuse, Italy, on the island of Sicily, Archimedes spent most of his life here, spreading his influence and genius among the city. Many of his inventions, ranging from pulleys used on ships to the Archimedes screw that is still used today in developing countries for obtaining water, were notable and revolutionary to the ever-changing world. In serving his city, Archimedes used his mind to invent machines that would help defend Syracuse against foreign attacks. Inventions such as the Archimedes claw that was used to tip over ships, the Archenteron, which was a steam-powered cannon, and the Archimedes death ray, which was used as a burning glass to set foreign ships within bow and arrow range of fire, were all used to defend Syracuse. Although these inventions were technological feats for their time, Archimedes was killed by a Roman soldier in the siege of Syracuse by the Romans in 212 BC. Our group wanted to focus in and explore the Archimedes death ray and the physics behind this invention to see if this was possible for burning enemy ships.
Deeper into the physics of this myth. For our experiment, we used two types of mirrors, a concave mirror and a flat mirror. The physics of the sunlight and how it was manipulated can be explained through a visualization technique called a ray diagram. When using the sun as a light source, this is different from what we're used to doing in lab because the sun is a light source is a lot farther away than, say, the lasers we use in lab experiments. Since the sun is farther away, the light rays coming from the sun that actually hit the mirror and reflect off of it are essentially parallel, which looks a little something like this. For a concave mirror, the ray diagram looks like this. Notice how all the rays are coming in parallel, so they would all reflect off the concave mirror through the focal point, creating a concentration of light at the focal point, which is where we placed our boat. For flat mirrors, the ray diagram looks a little different. The mirrors were arranged as shown. All of these mirrors are flat mirrors, so they have a certain way of reflecting light. The light rays still come in parallel, as the source hasn't changed, but when they hit the mirror, the light will reflect off of the mirror at an angle that will be exactly double the angle of the incoming light and the imaginary line perpendicular to the plane of the mirror. The flat mirrors reflect light in such a way that we can see where the reflected ray comes off of the mirror in the form of light. So when we arranged the mirrors, we adjusted the mirror so that all of the reflected rays were concentrated on the boat. The ignition temperature of wood is about 180 degrees Celsius or 356 degrees Fahrenheit. So for the sun to light the boat on fire, starting when the boat is at room temperature, or about 23 degrees Celsius, the sun would have to heat up the boat about 160 degrees Celsius or about 283 degrees Fahrenheit hotter than room temperature. To calculate that temperature difference, we'll need to calculate the total energy difference. We do that by using the equation E equals solar irradiance times area. The solar irradiance is the radiant energy from the sun that reaches the Earth's surface, which, according to NASA, is about 1,366 watts per meter squared at the zenith. This will stay constant no matter what, since the sun is a constant source of light energy. The area will depend on which type of mirror we use. For the concave mirror, we calculate that the surface area is about 0.2284 meters squared. Therefore, the energy calculated is about 312 joules. Converting that to degrees Celsius, we come up to 0.164 degrees Celsius difference. But that's only for 1 second of exposure. We expose the boat to a concave mirror for about 10 minutes. So we're going to multiply that number by 600 seconds to get a final temperature difference of 98.57 degrees Celsius. Adding that to our original room temperature of 23 degrees Celsius brings our final temperature to 121.57 degrees Celsius, well below the ignition temperature of the wood. And if we use our same method of calculations for the flat mirror arrangement, scaling the 10 rectangular mirrors and the 2 circular mirrors, we get a temperature difference of 41.32 degrees Celsius. Adding this to the boat at room temperature gives us a final temperature of 64.327 degrees Celsius, barely half the original ignition temperature.
Initially, we used a concave mirror. The mirror is 54 centimeters wide. We held it standing half a meter away from the boat, ensuring that the focal point would be oriented on the middle of the ship. We held this orientation for 10 minutes. Being recreated multiple times with varying results, there is a multitude of models on how to go about conducting this experiment. Our primary setup of using a concave mirror was based off the observations we had made in class, using mirrors and their reflective properties. Using a model from a class at MIT that conducted this experiment back in October of 2005, the secondary setup of mirrors, along with a time constraint, were implemented into this experiment. We used 10 by 7.5 centimeter flat mirrors and two 11.5 diameter circular flat mirrors in a semicircle configuration with each mirror's focal point fixed on the boat. Once again, we held this mirror orientation for 10 minutes. In our two experiments, we failed to get ignition of our boat using the two setups. After 10 minutes of waiting on each setup, while there was a noticeable change in temperature once the boats were exposed to the light reflected off the mirrors, they were nowhere close to ignition. This change in temperature was larger in the second setup than in the first setup. There were several factors that we feel could have contributed to our failed attempts. If we were able to replicate the experiment again, we would first look at getting more concave mirrors. With more rays being focused on the boat, the sail would reach ignition quicker. Another way we could have improved this experiment was by holding the mirror orientations for longer periods of time. Since we only waited 10 minutes for each setup, redoing these trials with a longer time period could have resulted in a larger temperature increase leading to ignition. We also could have used proper stands to orient the flat mirrors used. This would allow us to get the most accurate orientation of the mirror that would allow us to focus all the reflected rays on a very specific part of the boat, increasing its chances of reaching the temperature of ignition.